March 10, 1945. The eastern bank of the Rhine River near Remagen, Germany. Captain James Gamble of the 291st Engineer Combat Battalion watched his men unload steel panels from deuce-and-a-half trucks, each section 10 feet long and weighing less than 600 pounds. The Ludendorff Bridge, the railway span American forces had miraculously captured intact 3 days earlier, groaned under the weight of Sherman tanks crossing single file. Engineers had already detected structural cracks. The bridge could collapse at any moment. Gamble's orders were clear: construct an alternate crossing before the captured bridge failed. But the equipment arriving didn't look substantial enough to support 40-ton tanks. Each panel seemed too light, too simple. Prefabricated steel sections that 6 men could carry, assembled without cranes or heavy machinery. No permanent foundations, no concrete piers, just modular components that fit together like an oversized construction toy. The design contradicted everything traditional engineering taught about bridge construction. Yet within 10 hours, Gamble's battalion had assembled 1,032 feet of bridge spanning the Rhine, a pontoon causeway strong enough to carry Sherman tanks, built entirely by hand from panels that arrived in trucks like flat-pack furniture. What American tank commanders crossing that improvised span didn't realize was that they were driving across a bridge designed by a British civil engineer whose War Office superiors had initially rejected his concept as too simple, too unorthodox, too far removed from accepted military engineering doctrine. The Rhine crossing, and with it, the Allied advance into Germany's industrial heartland, depended on modular steel panels a committee of experts had once dismissed as impractical. Chapter 1. The Engineer. Nobody wanted the Rhine crossing, and with it, the Allied advance into Germany's industrial heartland, depended on modular steel panels a committee of experts had once dismissed as impractical. But 5 years earlier and 800 miles northwest, those panels existed only as sketches on drawing paper in a modest workshop. Christchurch, England, 1940. Donald Coleman Bailey sat at his workbench long after sunset, drafting designs that contradicted every principle his War Office superiors held about military bridge construction. At 42 years old, Bailey was a civil servant at the experimental bridging establishment, senior enough to understand institutional thinking, junior enough that his ideas received polite dismissal rather than serious consideration. His concept seemed almost childishly simple: standardized steel panels 10 feet long, 5 feet high, weighing approximately 570 pounds each. No rivets, no welding, just pre-drilled holes accepting steel pins that locked panels together. 6 men could carry each section. Dozens of panels could stack on a standard 3-ton lorry. Assembly required only soldiers following basic instructions, no specialized equipment, no engineering degrees, no permanent foundations. Bailey had conceived the design in 1936, presenting detailed calculations to War Office review committees, who examined the proposal with professional skepticism that bordered on dismissal. Senior engineers preferred established systems: pontoon bridges requiring specialized boats and trained crews, or complex truss bridges assembled by Royal Engineers with technical expertise ordinary infantry didn't possess. The committee's objections carried institutional weight. Bailey's modular design seemed insufficiently robust for military loads. The pin connection system appeared too simple compared to traditional riveted or welded structures. The standardized panels looked inadequate for the varied span lengths and load requirements armies encountered in combat. One reviewer summarized the consensus: interesting theoretical exercise, but insufficiently practical for field deployment. Bailey returned to routine duties, designing conventional military equipment, supervising tests, filing reports. But evenings found him back at his workshop, refining calculations, testing panel joints with prototype sections he fabricated in his garage. The design worked. Mathematics confirmed it. Small-scale models demonstrated it. Yet institutional inertia blocked further development. Then came Dunkirk, May-June 1940. The British Expeditionary Force evacuated France, abandoning every piece of heavy equipment on the beaches, including all military bridging systems. 338,000 soldiers escaped, but the Army lost tanks, artillery, vehicles, and, critically, the specialized bridging equipment necessary for crossing rivers during offensive operations. The War Office suddenly faced crisis that made theoretical bridge designs intensely practical. Britain needed portable bridge systems that could be manufactured quickly, transported easily, and deployed by ordinary soldiers without specialized training or equipment. Traditional pontoon bridges required boats destroyed at Dunkirk. Complex truss systems needed trained engineers scattered across evacuated units. In late 1940, the War Office convened emergency conference on temporary bridging capable of handling heavy loads. Bailey's rejected design received second examination, this time driven by desperate urgency rather than institutional skepticism. The same panels dismissed as too simple now represented precisely what circumstances demanded: standardization enabling mass production, simplicity allowing rapid field assembly, modular flexibility adapting to varied tactical requirements. The concept Bailey had sketched alone in his workshop, refined through evenings of unofficial work while superiors told him to focus on practical projects, became Priority War Office program. Approval came with startling speed. Production authorization followed within weeks. But approval meant nothing, without proof. Bailey faced new challenge more demanding than institutional skepticism, demonstrating that panels dismissed by experts could actually support 40-ton tanks under combat conditions. The design worked in his garage workshop. Now it needed to work under military loads that would expose any weakness instantly and catastrophically. Chapter 2. The Prototype that changed warfare. Bailey faced new challenge more demanding than institutional skepticism, demonstrating that panels dismissed by experts could actually support 40-ton tanks under combat conditions. The design worked in his garage workshop. Now it needed to work under military loads that would expose any weakness instantly and catastrophically. May 1941, Christchurch, Dorset. The experimental bridging establishment assembled Donald Bailey's full-scale prototype on the grounds where theory would face reality. Each steel panel measured exactly 10 feet long by 5 feet high, weighing 570 pounds. The weight seemed contradictory, heavy enough to require 6 men for carrying, yet light enough that ordinary infantry could transport dozens on 3-ton lorries without specialized lifting equipment. The panels connected through elegantly simple mechanism, pre-drilled holes accepting steel pins that locked sections together, no rivets requiring pneumatic tools, no welding demanding skilled labor and portable generators, just pins inserted through aligned holes secured by retention clips. A soldier with basic instructions could connect panels as easily as assembling children's construction toys, though the loads these toys would carry exceeded anything children imagined. Bailey's design incorporated flexibility that traditional bridges lacked. Single panels could span short gaps. For longer distances or heavier loads, engineers could stack panels in double-double configurations, 2 panels high, 2 panels wide, quadrupling load capacity. Triple-triple arrangements supported the heaviest tanks. The modular system adapted to tactical requirements through simple mathematics. More panels meant greater strength. War Office observers gathered at the test site with professional skepticism barely concealed. These men had reviewed and rejected Bailey's proposal years earlier. Now circumstances forced reconsideration, but institutional doubts persisted. Could panels connected by pins really support 40-ton tanks? Traditional military bridges used robust construction, welded steel trusses, concrete piers, foundations engineered for permanent installations. Bailey's design looked temporary, improvised, insufficiently substantial. The test protocol was brutal. A 30-foot span assembled by untrained soldiers, infantrymen given basic instructions but no engineering training. Time limit, 4 hours, generous by military standards but challenging for men unfamiliar with the system. Success criteria supporting Mark Vave tank loaded with pig iron to simulate full. Combat weight, approximately 40 tons. Assembly began at 08 Mo. Soldiers manhandled panels into position, aligned pre-drilled holes, inserted connecting pins. The simplicity that had caused rejection became operational advantage. No specialized tools required, no technical calculations beyond pin goes through hole. Mistakes were self-evident. Misaligned panels wouldn't accept pins, and easily corrected. Traditional military bridges required trained engineers interpreting complex assembly diagrams. Bailey's design needed only soldiers following instructions simple enough to execute under combat stress. By 10 Mashon 2 hours after starting, the 30-foot span was complete, half the allotted time. The observers exchanged glances that mixed surprise with residual skepticism. Speed was impressive, but strength mattered more. A 40-ton tank would test whether simplicity had compromised structural integrity. The Mark V approached at walking speed, tracks clanking against steel decking laid across the panels. Engineers monitored deflection. Any span sags under load, but excessive deflection indicates structural failure. Bailey's calculations predicted 6 inches of sag for the test configuration. Measurements confirmed 5.8 inches maximum deflection as the tank reached midspan. The bridge held, no pins sheared, no panels buckled. The structure that looked too simple to work performed exactly as mathematics predicted. Production authorization came within weeks. Factories across Britain, over 650 firms including companies that manufactured window frames, canoe paddles, anything but bridges, retooled for panel production. Standardization meant parts from different factories were interchangeable. By July 1941, production reached industrial scale. By December 1st, Bailey bridges deployed to North Africa, where British 8th Army faced Rommel's Afrika Korps across Libya's Wadis and escarpments. Field Marshal Bernard Montgomery encountered Bailey bridges during Operation Crusader, the November-December 1941 offensive to relieve Tobruk. His armor crossed Wadis on spans assembled in hours rather than days. Traditional bridges required. The tactical advantage was immediate. German forces couldn't establish defensive lines when British tanks bypassed destroyed bridges through rapid Bailey construction. Montgomery's assessment carried weight that technical demonstrations couldn't match. "The Bailey Bridge is the best thing in the war," he declared after watching engineers span a wadi under fire, enabling his tanks to maintain pursuit of retreating German forces. The endorsement from Britain's most prominent field commander transformed Bailey's design from experimental system to critical military technology. The simplicity that War Office committees had dismissed as insufficient now proved revolutionary. Traditional military bridges required specialized equipment, trained engineers, days of construction. Bailey bridges needed trucks, panels, and infantry with basic instructions. The design that began as sketches on an envelope, refined through unofficial evening work in a Christchurch workshop, had become the engineering innovation that would carry Allied armor across every major river in Western Europe. But the ultimate test remained ahead. Rhine River crossings against determined German resistance, where minutes could mean the difference between bridgehead and catastrophe. Chapter 3. From Sicily to Normandy. But the ultimate test remained ahead. Rhine River crossings against determined German resistance, where minutes could mean the difference between bridgehead and catastrophe. First, Bailey's design had to prove itself across the rivers and wadis of 3 continents. July 10, 1943. Allied forces invaded Sicily. German and Italian defenders executed textbook defensive doctrine: retreat slowly, destroying every bridge during withdrawal, forcing attackers to halt at each river while engineers constructed crossings. The strategy had worked throughout military history. Rivers without bridges stopped armies for days, while defenders established new positions. But Montgomery's 8th Army and Patton's 7th Army carried something German intelligence hadn't accounted for: trucks loaded with Bailey bridge panels. When British armor reached the Simato River on July 15th and found the bridge demolished, Royal Engineers assembled a replacement in 4 hours. German forces hadn't completed their defensive positions. The tanks kept advancing. Across Sicily, the pattern repeated. Germans destroyed a bridge. Allied engineers arrived hours later with panels, pins, and basic instructions. Spans appeared faster than German forces could retreat to next defensive line. The tactical mobility advantage was decisive. Armies that could bridge rivers in hours rather than days maintained pursuit pressure that prevented enemy from establishing stable fronts. The Italian campaign tested Bailey bridges under increasingly demanding conditions. Rivers in Sicily averaged 30 to 60 feet wide. Italy presented wider obstacles. The Volturno River north of Naples measured 120 feet at crossing points. Engineers deployed triple panel configurations: 3 panels high, 3 panels wide, creating structures supporting the heaviest Sherman tank variants at weights approaching 50 tons. November 1943. Royal Engineers constructed a Bailey span across the Sangro River in eastern Italy. 1,126 feet, the longest yet attempted. The bridge required pontoon supports at intervals, but the panels remained identical to those used for 30-foot spans. Modular standardization meant engineers could build bridges of any length using the same components trucked from supply depots. Field Marshal Montgomery's assessment evolved from tactical appreciation to strategic endorsement. Bailey bridging made an immense contribution towards ending World War II, he wrote in 1947 post-war memoir. As far as my own operations were concerned, with the 8th Army in Italy and with the 21 Army Group in Northwest Europe, I could never have maintained the speed and tempo of forward movement without large supplies of Bailey bridging. By June 1944, over 3,000 Bailey bridges operated in Sicily and Italy alone, 55 miles of bridging averaging 100 feet per span. The system that War Office committees had rejected as too simple had become the infrastructure enabling Allied advance up the Italian peninsula despite German demolition expertise. D-Day planners studied the Italian experience and drew critical conclusions. German defenders would destroy every bridge in Normandy during the retreat that would inevitably follow Allied breakthrough. Traditional military engineering couldn't maintain the operational tempo necessary to exploit breakthroughs before Germans established new defensive lines. Success required bridge construction capability matching the speed of tank advance. Bailey bridge components were pre-positioned in England months before invasion. Trucks loaded with panels, pins, and decking rolled off landing craft onto Normandy beaches within hours of initial assault. The first Bailey Bridge in Normandy, London Bridge, was constructed across the Caen Canal at Benouville on the night of June 7, 1944, by British Royal Engineers working under sporadic German artillery fire. Within 48 hours of D-Day landings, multiple Bailey bridges spanned Norman rivers and canals. The engineering speed transformed tactical situation. Allied armor advanced inland faster than German commanders anticipated. Defenders couldn't establish coherent front lines when attackers bridged obstacles hours after defenders destroyed existing infrastructure. The Battle of Normandy consumed 3 months of brutal fighting through hedgerow country, where every field became battlefield. During those 3 months, engineers constructed 30 Bailey bridges in the vicinity of Caen alone. Each span enabled tank movements that outflanked German defensive positions organized around blown bridges. The modular system operated at industrial scale. Over 600 firms manufactured panels, producing 200 miles of bridges comprising 700,000 panels during the war. By August 1944, when Allied forces broke out from Normandy and raced across France toward German border, over 2,000 Bailey bridges operated in France. The rejected design that Donald Bailey had sketched in his Christchurch workshop now formed the infrastructure supporting the largest mechanized offensive in human history. The simplicity that had seemed insufficient to military experts proved to be decisive operational advantage. German engineers could destroy bridges. Allied engineers could replace them faster than Germans could retreat to next river line. The mathematics of pursuit versus retreat had fundamentally changed, but one river remained that would test Bailey bridges beyond all previous challenges. The Rhine, 300 to 1,200 feet wide, swift current, historically impregnable defensive barrier. German doctrine called for destroying all Rhine bridges during any retreat into the Reich. Allied planners knew Bailey bridges could theoretically span any width the Rhine presented. The question wasn't technical capability. It was whether opportunity would arise before German demolitions sealed the border. That opportunity would come in March 1945 at a railway bridge near the town of Remagen, through combination of German failure and American speed that would require every lesson learned from Sicily to Normandy to exploit before the window closed. Chapter 4. The Rhine, Germany's last fortress. That opportunity would come in March 1945 at a railway bridge near the town of Remagen, through combination of German failure and American speed that would require every lesson learned from Sicily to Normandy to exploit before the window closed. But first, the obstacle needed understanding. The Rhine wasn't just another river, it was Germany's last defensible frontier, a natural barrier that had stopped invasions for 2 millennia. March 1945. The river varied from 300 feet wide at narrow points to over 1,200 feet at strategic crossing sites. Swift current ranging from 5 to 10 knots depending on season and location. Heavily defended eastern bank where German forces held prepared positions. Western approaches swept by artillery pre-registered on every conceivable crossing point. German military doctrine was unambiguous. Every Rhine bridge would be destroyed during any retreat into the Reich. Demolition charges were placed on all major spans months in advance. Engineer units received orders to blow bridges the moment Allied forces approached within striking distance. The Rhine would become an uncrossable moat protecting Germany's industrial heartland. Traditional military bridging offered no solution. Pontoon bridges required days of assembly, specialized equipment, and left engineering crews exposed on open water under German artillery observation. The Rhine's width exceeded most standard military bridging spans. Combat engineers would need to construct approaches, assemble floating sections, anchor against strong current, all while under fire from entrenched defenders on the eastern bank. Historical precedent supported German confidence. Roman legions established Rhine frontier that held for centuries. Napoleon's armies crossed in 1805 but required extensive preparation. World War I offensives never breached the Rhine. The armistice came before Allied forces reached Germany's border. For 2,000 years, the Rhine had represented the line where invasion stalled. Allied planners studied the problem through winter 1944-1945 and reached conclusion that depended entirely on Bailey bridges. The modular system could theoretically span any width the Rhine presented. Multiple Bailey pontoon bridges could be constructed simultaneously at different crossing points. Speed of assembly might enable establishment of bridgeheads before German counterattacks could eliminate them. But theory required opportunity. If Germans executed demolition doctrine, Allies would face contested river crossings against prepared defenses, casualties measured in thousands, delays measured in weeks. The Rhine crossing could become the costliest battle of the Western European campaign. Then opportunity arrived through accident rather than planning. March 7, 1945, 1550 hours. Soldiers of the 9th Armored Division's 27th Armored Infantry Battalion approached Remagen, a small town 40 kilometers south of Cologne. Intelligence suggested the Ludendorff Bridge, a double-track railway span built 1916 and 1918, had already been destroyed. German doctrine demanded it. Every other Rhine bridge had been blown. But through combination of German communication failures, command confusion, and desperate courage by American infantry, the Ludendorff Bridge stood. Demolition charges detonated but failed to drop the span. Within minutes, American soldiers were crossing, the first Allied troops on the eastern bank of the Rhine since Napoleon's legions 140 years earlier. The capture made front-page news in American newspapers. General Eisenhower immediately altered strategic plans. The unexpected bridgehead more than 2 weeks ahead of scheduled Operation Plunder allowed rapid reinforcement. 5 divisions began moving toward Remagen, but American engineers inspecting the captured bridge detected problems immediately. The failed German demolition attempt had damaged structural members. Months of Allied bombing, 33 bomber raids had targeted the span since October 1944, had weakened steel supports. Artillery near misses had cracked masonry approaches, and now the bridge carried traffic it was never designed to support. Sherman tanks, heavy artillery, trucks loaded with ammunition, all crossing single file at intervals measured in minutes rather than the hours traditional railway bridges required between trains. Engineers measured deflection, examined rivets, calculated load stresses. Their assessment was unequivocal. The Ludendorff Bridge was failing. Cracks widened hourly under continuous tank traffic. The span could collapse at any moment. If it fell before alternate crossings were established, the entire bridgehead, thousands of American soldiers on the wrong side of the Rhine, would be cut off, vulnerable to German counterattacks without armor support or resupply. The window was closing. Bailey bridges represented the only solution. Panels and pontoons were already en route, trucks carrying components forward from supply depots. But time was the constraint that mathematics couldn't solve. Could engineers assemble a Bailey span over 1,000 feet across the Rhine's swift current before the captured bridge collapsed? The race was on, and Captain James Gamble's 291st Engineer Combat Battalion received orders that would determine whether the Remagen bridgehead survived or became an isolated disaster costing thousands of lives. Chapter 5. 10 Hours to Victory. The race was on, and Captain James Gamble's 291st Engineer Combat Battalion received orders that would determine whether the Remagen bridgehead survived or became an isolated disaster costing thousands of lives. March 10, 1945, 20 hours. Engineers surveying the Ludendorff Bridge delivered a verdict that confirmed everyone's fears. The span was failing catastrophically. New cracks appeared hourly. Steel support members groaned audibly under each passing tank. Load calculations showed the structure operating beyond safe limits. Collapse wasn't a possibility. It was inevitable. The only question was when. Captain Gamble received emergency orders. Construct Bailey Pontoon Bridge 1,000 feet downstream before the captured span failed. The location had been selected hours earlier. River width approximately 1,032 feet. Current moderate eastern bank already secured by infantry establishing the bridgehead. Trucks carrying Bailey components were already arriving. Steel panels weighing 570 pounds each. Pontoon floats, connection pins, timber decking. Assembly began at dusk. Engineers worked under portable spotlights that illuminated the construction site and made perfect aiming points for German artillery observers on heights east of the river. The first shells arrived within 30 minutes. High explosive rounds bracketed the worksite, adjusted closer with each salvo. Men died. Others took their places. The simplicity Donald Bailey had designed into his bridge system became life-saving advantage under combat conditions. Traditional military bridges required trained engineers executing complex assembly procedures. If key personnel were killed, construction halted until replacements with equivalent expertise arrived. Bailey bridges needed only soldiers who could follow basic instructions. Align panel, insert pin through pre-drilled hole, secure with retention clip, repeat. When artillery killed a 6-man panel carrying team, infantry replacements stepped forward. Officers shouted instructions over shell fire. The work continued. Panels connected systematically despite casualties. The modular system was forgiving. Mistakes were self-evident and easily corrected without specialized knowledge. Pontoons were positioned at intervals across the river, anchored against current. Bailey panels were assembled on the western bank in sections, then pushed out over the pontoons. The process resembled giant construction toy being assembled by men working in darkness under artillery fire, replacing fallen comrades while maintaining systematic panel-pin-panel rhythm that would span over 1,000 feet of Germany's most formidable natural barrier. Midnight passed. German artillery intensified. Wehrmacht commanders recognized what American engineers were building and committed every available gun to stopping it. Counter-battery fire from American artillery suppressed some German positions, but couldn't eliminate the threat. Shells continued falling. Casualties mounted. The work continued. By 06 March 11th, 10 hours into construction, the span had reached three-quarters completion. Engineers working on the eastern approach came under small arms fire from German infiltrators. Infantry secured the perimeter while bridge construction proceeded without pause. The timeline was inflexible. Ludendorff Bridge could collapse at any moment. At 10 a.m. March 11, 1945, exactly 10 hours after assembly began, the final panel locked into position. The bridge was complete, 1,032 feet spanning the Rhine River, assembled by soldiers under artillery fire, built from components carried in trucks, connected by pins through pre-drilled holes. First Sherman tank approached at 10:30 a.m. The driver hesitated. Every soldier knew bridges could collapse under combat loads. Engineers had calculated load capacity, but calculations weren't certainty. The tank commander ordered forward. Tracks clanked against timber decking. The bridge held. 40 tons crossing 1,032 feet of modular panels designed in a British civil servant's garage workshop, assembled in 10 hours by infantry under fire. The relief was momentary. At 3 p.m., Ludendorff Bridge collapsed. The grinding crash echoed across the valley as steel and stone plunged into the Rhine. 28 American engineers working on structural repairs died in the collapse. Hundreds more would have died if the span had failed hours earlier when tank traffic was heaviest. The Bailey Bridge, constructed in desperation, assembled under fire, completed with hours to spare, became the sole Rhine crossing point for the entire 9th Armored Division. 5 divisions queued on the western bank, waiting to cross into the bridgehead. Single-lane traffic created bottleneck that extended operations for days beyond optimal schedules. But the bridgehead held. German counterattacks couldn't eliminate forces east of the Rhine when armor and artillery continued crossing despite Ludendorff's collapse. The engineers who died building that span, and the 28 who died when Ludendorff collapsed, had maintained the bridgehead through sacrifice and through exploitation of simple engineering that institutional experts had once dismissed as insufficiently robust. The panels carried by 6 men, connected by pins through pre-drilled holes, assembled without cranes or specialized equipment, had proven strong enough to carry the weight of an army across Germany's last natural defensive barrier. But one Bailey Bridge couldn't support the entire Allied offensive. The Rhine stretched hundreds of kilometers from Switzerland to the North Sea. If the Remagen bridgehead demonstrated what Bailey bridges could achieve under emergency conditions, Allied planners recognized that final victory required systematic Rhine crossing operations across the entire front. Multiple bridges, multiple crossing points, overwhelming German defensive capacity through engineering speed that Wehrmacht demolition doctrine couldn't counter. The race wasn't over. It was expanding to encompass the entire Rhine frontier. Chapter 6. Bridges Across a Nation. The race wasn't over. It was expanding to encompass the entire Rhine frontier. March 11-31, 1945. Remagen's success triggered systematic Rhine crossing operations across a 100-mile front. Allied commanders recognized that single bridgehead, despite its strategic value, created bottleneck that delayed exploitation. German resistance was collapsing, but Wehrmacht retained capability to defend established positions. Speed mattered. Multiple crossings would overwhelm German defensive capacity beyond recovery. Field Marshal Bernard Montgomery planned Operation Plunder with methodical precision that contrasted sharply with Remagen's opportunistic capture. British 5th Army Group would cross near Wesel on March 23-24, supported by massive artillery preparation, airborne assault, and systematic engineering that would establish permanent bridgehead before German counterattacks could organize. The artillery barrage began at $17 March 23rd, 4,000 Allied guns firing for 4 hours, devastating German defensive positions on the eastern bank. British bombers attacked Wesel simultaneously, reducing the town to rubble. At 21 Au, first assault troops crossed in Buffalo amphibious vehicles, establishing beachheads while engineer units prepared bridge construction sites. March 26-28, Royal Canadian Engineers constructed Blackfriars Bridge near Rees, the longest Bailey Bridge built during World War II. 1,814 feet spanning the Rhine, assembled in 2 days by Canadian engineering units working around the clock. The span required multiple pontoon supports anchored against swift current. Triple panel configurations supported the heaviest armor. The structure that began as Donald Bailey's rejected concept now stretched over 1,800 feet. Nearly 600 yards of modular panels connected by pins through pre-drilled holes. Simultaneously, U.S. Third Army under General George Patton crossed at Oppenheim on March 22nd, 1 day before Montgomery's massive Operation Plunder. Patton's engineers constructed multiple Bailey bridges enabling armored divisions to exploit breakthrough into southern Germany. The competitive timing wasn't accidental. Patton wanted credit for crossing Rhine before Montgomery's meticulously planned operation. Within 3 weeks of Remagen's capture, 7 major Bailey bridges spanned the Rhine. Additional pontoon bridges, treadway spans, and captured bridges supplemented the crossings. By month's end, over 25 Allied divisions operated east of the Rhine, American, British, Canadian, French forces advancing on multiple axes deeper into Germany's industrial heartland. German resistance collapsed systematically. Wehrmacht doctrine depended on using natural obstacles, rivers, mountains, prepared defensive lines, to delay Allied advance while reserves concentrated for counterattacks. The strategy required time. Demolishing bridges bought days for defenders to establish new positions. But Bailey bridges eliminated that advantage. Allies bridged obstacles within hours. German forces couldn't establish coherent defensive lines when attackers maintained constant pressure through engineering speed that Wehrmacht demolition doctrine couldn't counter. The tactical mathematics had fundamentally shifted. Traditional military logic held that armies slowed at rivers. Engineers required days to construct crossings. Defenders used that time to fortify new positions. But modular bridge components carried in trucks, assembled by infantry following basic instructions, completed spans faster than defenders could retreat to next obstacle. By April 1945, Allied tank columns operated 200 miles inside Germany. The Rhine, unconquered for 2 millennia, the barrier that stopped Roman legions and Napoleon's armies, had been crossed at will by forces carrying bridge components in 3-ton lorries. The river that German propaganda described as impregnable frontier protecting the fatherland had become tactical inconvenience solved through simple engineering in hours rather than strategic obstacle requiring weeks. Over 3,000 Bailey bridges now operated across Western Europe, totaling more than 500 miles of span. The rejected design that War Office committees dismissed as too simple had become the infrastructure supporting the largest mechanized offensive in history. Factories that manufactured window frames and canoe paddles had produced 700,000 panels, enabling armies to cross rivers as casually as crossing streets. The simplicity remained revolutionary. 6 men carried panels weighing 570 pounds. Pins connected through pre-drilled holes. No welding, no rivets, no specialized equipment. Yet those panels supported 40-ton tanks crossing 1,000-foot spans, assembled in hours by soldiers under fire. The design Donald Bailey sketched in his Christchurch workshop, working nights after superiors told him to focus on practical projects, had enabled final defeat of Nazi Germany by transforming rivers from obstacles into footnotes. General Dwight D. Eisenhower would later assess the Bailey Bridge's contribution with characteristic directness. Without the Bailey Bridge, we should not have won the war. The statement wasn't hyperbole. Allied victory in Northwest Europe depended on mobility advantage that Bailey bridges enabled, crossing rivers faster than enemies could destroy infrastructure, maintaining operational tempo that prevented defensive stabilization, exploiting breakthroughs before counterattacks could seal penetrations. The rejected civilian design had proven more valuable than any weapon system, more decisive than any tactical innovation. And its legacy would extend far beyond the Rhine crossings into conflicts and construction projects spanning continents and decades. Chapter 7. The Bridge That Won the War. The rejected civilian design had proven more valuable than any weapon system, more decisive than any tactical innovation. And its legacy would extend far beyond the Rhine crossings into conflicts and construction projects spanning continents and decades. General Dwight D. Eisenhower surveyed the ruins of Nazi Germany from headquarters that coordinated the final Allied advance. The victory had been total. Wehrmacht shattered, Reich divided into occupation zones, Hitler dead in his Berlin bunker. But Eisenhower understood that victory resulted not merely from courage or firepower, but from technological advantages that multiplied military effectiveness. His post-war assessment carried weight that technical demonstrations couldn't match. Without the Bailey Bridge, we should not have won the war. The statement wasn't diplomatic courtesy or hyperbole. It reflected strategic reality. Allied victory in Northwest Europe depended on mobility advantage that Bailey bridges enabled, crossing rivers faster than enemies could destroy infrastructure, maintaining operational tempo that prevented defensive stabilization, exploiting breakthroughs before counterattacks could seal penetrations. The mathematics were undeniable. Over 3,000 Bailey bridges operated across Western Europe by war's end, totaling more than 500 miles of span. 700,000 panels manufactured by 650 firms, most of which had never built bridges before standardization allowed window frame factories and canoe paddle manufacturers to produce interchangeable military engineering components. The system that War Office committees dismissed as too simple had become the infrastructure supporting mechanized warfare at industrial scale. Donald Coleman Bailey received knighthood from King George VI for services to military engineering. Sir Donald Bailey, the 48-year-old civil servant who'd sketched revolutionary designs on evenings, while institutional experts told him to focus on practical projects. The recognition validated not merely the bridge design, but the principle that innovation often emerges from outside official channels, from individuals working unofficially, because established authorities cannot recognize solutions that contradict accepted doctrine. Bailey returned to civilian life, continuing work at the Road Research Laboratory until retirement. He rarely discussed his wartime contribution publicly, maintaining the modest demeanor of civil servant who'd simply solved engineering problem that needed solving. But his design continued serving long after WOE ended. Korean War 1950-1953. Bailey bridges crossed the rivers of the Korean Peninsula, enabling United Nations forces to maintain supply lines and tactical mobility against North Korean and Chinese armies. The panels that spanned the Rhine proved equally effective spanning the Imjin River and countless smaller obstacles in mountainous terrain where traditional bridging would have been impossible. Vietnam War, 1965-1973. American engineers constructed Bailey bridges throughout South Vietnam, replacing infrastructure destroyed by combat or neglect. The modular system adapted to tropical conditions, monsoon flooding, and combat damage with same flexibility that made it effective in European campaigns. Civilian applications multiplied globally. Disaster relief organizations stockpiled Bailey components for rapid deployment after floods, earthquakes, hurricanes destroyed infrastructure. Remote mining operations used Bailey bridges to access resources across rivers where permanent bridge construction was economically unfeasible. Construction companies employed the system for temporary spans during permanent bridge maintenance. Modern military bridges still use principles Bailey invented: modular components allowing flexible configuration, hand assembly without specialized equipment, truck transport enabling rapid deployment. The medium girder bridge MGB, developed by British Army in 1960s, directly descended from Bailey's design. The Maybe logistical support bridge used by NATO forces represents evolutionary refinement of concepts Bailey sketched in 1936. Museums preserve Bailey bridge panels as historical artifacts documenting technological innovation that changed warfare. Imperial War Museum in London displays original panels alongside photographs of Rhine crossings. Canadian War Museum in Ottawa features Blackfriars Bridge documentation, the 1,814-foot span that remains longest Bailey bridge built during Wadiyari. U.S. Army Engineer Museum at Fort Leonard Wood maintains working Bailey bridge sections for training and historical demonstration. Visitors touch steel panels weighing 570 pounds, reading plaques explaining how 6 men could carry them, how pins connected through pre-drilled holes without welding or rivets, how spans up to 200 feet could be assembled in hours by ordinary soldiers following basic instructions. The simplicity seems almost childish, oversized construction toy connecting through pins and holes. Yet those simple components supported 40-ton tanks crossing 1,000-foot spans assembled under artillery fire. The contrast between simplicity and capability reveals why innovation often faces institutional resistance. Experts invested in complex systems cannot recognize revolutionary solutions that appear deceptively simple. War Office committees reviewing Bailey's proposal in 1938 saw inadequately robust design insufficient for military requirements. They couldn't envision how simplicity itself would become operational advantage, enabling mass production, rapid assembly, and deployment by non-specialists. The pattern repeats throughout military history. Institutional authorities favor complexity, specialized equipment, established procedures requiring trained experts. Innovative designs challenging those assumptions face skepticism precisely because they simplify rather than complicate. Bailey's modular panels seemed insufficiently sophisticated compared to traditional bridges requiring engineers, specialized equipment, permanent foundations. The committees couldn't see that sophistication was liability rather than asset when tactical situations demanded speed over permanence. The Rhine crossing depended on design created in a garage workshop by a 42-year-old civil servant whose superiors told him to focus on practical projects. The rejected innovation proved more valuable than any institutionally approved military engineering system. The unauthorized evening work produced technology that Supreme Allied Commander credited with winning the war. The lesson extends beyond Bailey bridges to fundamental questions about innovation, institutional authority, and how organizations recognize solutions that contradict established thinking. Revolutionary advances often come from margins rather than centers, from individuals working outside official channels, because established experts cannot perceive value in approaches that challenge accepted doctrine. Donald Bailey died in 1985, age 83. His obituaries described him as modest civil servant who changed warfare through simple engineering solution that committees of experts had rejected. The steel panels connecting through pins and holes, the design dismissed as too simple, had bridged rivers across 5 continents, enabling armies to cross obstacles that stopped invasions for millennia. The bridge that won the war began as sketches on paper in a Christchurch workshop, refined through evening work, while institutional authorities focused on practical designs that required what wars couldn't provide: time, specialized equipment, trained experts. Bailey gave armies what they needed: speed, simplicity, and capability to turn rivers into footnotes rather than strategic obstacles. The rejected design became the bridge that carried victory across the Rhine, and the legacy that reminds each generation that innovation often wears overalls rather than uniform, works in workshops rather than offices, and solves problems through simplicity that experts mistake for insufficiency.